let's see. So, once your tablet is open, if you can go to Microsoft Teams, you want to make sure you pick the work or school version. I don't think it matters if you pick the updated version or the classic edition. So easiest place to usually get that is just from the search bar there at the bottom. Once you have that, you should see a tile for 4th hour AP Calculus. I loaded everybody's name in yesterday. So you should all have that. It should be there for everybody. If it's not, holler at me and we can fix that. But unless I made a mistake, I think I should have everybody in. Once you see that tile, go ahead and click on it. From this navigation pane here on the left, you're going to want to pick Class Notebook. Take a minute for the OneNote pane to load in there at the right. And then from there, if you see this little editing button on the right, there's a drop down. From that drop down, pick Open in Desktop, and that should load in your new notebook. Did you get it? Okay. We'll figure it out, Christian.
Well, if you say you can't add pages to this section because it's read only, it's just like an error.
That's okay. It's okay. It's the content library is what you're looking at?
Yeah.
Yeah, you've never been able to add pages there. It just was empty. Yes. Yes. That's fine. Will you pull that door shut on your way, though, too? Thank you. Now, that you've opened your new 4th hour notebook, my suggestion to you would be to, if you think you still want the stuff in your first semester notebook, to move that content to a non-shared notebook and then close your first semester notebook. Or if you don't think you want that content, just again, to just close your first semester notebook. I went and when I moved this all over, I have all the notes from first semester still in the content library. So those are still in there, everything that I wrote down. Now, your individual homework assignments obviously aren't going to be in your new notebook, but all the notes that I wrote may not have been from your section. I just picked one of the hours and just loaded those notes in, but we did the same thing. So it's like, it's virtually the same. But that's what you should see. If you don't see that stuff through, you might need to push a sync, and that content library should start coming through. I just noticed that I didn't move it or copy it over, so I just did it last hour. So depending on when you did it. Yeah, sure.
Do we have to copy things over from first semester?
No.
I was just going to save it as it was.
Yeah, you can just close the notebook and leave it.
Okay, because I think I'm going to use some of the content first semester, but I'm just saying, do we have to move it?
So what I saw a lot of in first semester was shared notebooks that were no longer active were causing syncing problems for people. So that's my suggestion would be, if you have stuff in first semester's notebook that you want to keep, to move that to a non-shared notebook and then close that shared notebook so you don't run into any weird syncing issue later on where it's trying to sync something that can't be synced because it's closed and your notebook stops syncing because of it and then you run into problems.
All right, got it. Thank you.
That was my suggestion. Again, there's nothing wrong with just closing the notebook and then reopening it later if you think that I do have something in there that I want that's about this. You can always like reopen the notebook and find it and get it. But that should take care of things. Now, the second semester syllabus is really the same as the first semester's. Class setup is going to be basically the same. The homework quizzes here at the start of class, you're going to also see, in addition to stuff from the previous homework assignment, I'm going to have some review stuff from first semester also that we'll do during that time. Because again, in preparation for that AP exam at the end of the course, I don't want that stuff from first semester getting kind of like too far away. So we will be doing practice still from first semester. It'll often take the place of, instead of having homework problem questions, it'll have like stuff from first semester. I won't tell you what the stuff is, but you have a partner. It'll probably be my AP questions that I'll have picked.
Accuracy?
Yeah, ish. Like 100% is not 10 needed for 10, but like some accuracy, sure. But like 70% 10, sure. Like the usual.
So it's not just on homework assignments. It's also on like review.
I would tell you if it's going to be on homework, and if it's not going to be on homework, it'll just be something from first semester. So that like that stuff just doesn't like drift away completely by the time the AP exam rolls around. You're like, oh my God, I don't remember anything from first semester. I want to kind of keep circling back to those ideas periodically so that it doesn't get too far. Does that make sense? Okay. The content for second semester we're going to cover, we have two sections that I wanted to finish in first semester we didn't get to. That's where we're going to start. So there are two like differentiation topics. We're going to do one of those today, and we'll do the next one Friday, and then differentiation is kind of done. The bulk of second semester is going to be spent doing integration. We'll talk about what that is, but it's basically the opposite of, it's like undoing a derivative. So we'll look at kind of how to do that and then applications of doing that. And that takes up the bulk of second semester. So we'll do all of chapters 5 and 6. We'll do parts of 9, 7, and 8 also. There will be some topics in second semester that I'm going to do that are not AB topics, that would be like BC topics. But as there's a lot of us that I think are planning on taking college calculus courses, a course or courses, where these topics are things that we should talk about. We're not doing the entire BC thing, but there'll be a topic or two that I introduce that we do that's technically a BC topic, but I think are important things to see. I will tell you beforehand of like, oh, this is a BC topic we're going to do today or whatever, but nothing we did in first semester would be considered a BC topic. Well, I mean, they're all BC topics, but they're also AB topics, right? The BC test and the AB test are almost the same test. It's like just a little bit more. Okay. Do you guys get your notebooks sorted here, loaded in and stuff? Okay. So today we're going to be talking about section 1.8. Oh, booger. Like a dummy, I loaded it in after I did my first hour lesson, so all my marks are still in here. That's okay. We'll figure it out. This topic is called Newton's method. And what Newton's method really is, it's a way to like approximate a solution to an equation. So you know on your calculator, when you graph something and you look and find the x-intercept, you know that function on your calculator? The way your what I suspect your calculator is doing to find that x-intercept is something similar to or equivalent to or some version of Newton's method. That is my suspicion. Now, I haven't looked at the actual programming to see exactly how it's doing this, but I'd be very surprised if it's not this method or something kind of equivalent to it. So the idea here, suppose you're looking for, the x-intercept of some function, essentially the solution to an equation set equal to 0. Everybody's okay with that? The way this works is you just guess at a solution. So you guess some x value that you think the solution might be. You find the point that corresponds to that x value on our function. And then we write the equation for the line tangent to the function at that point. And then you solve that equation, that tangent line equal to 0, to find the x-intercept for that tangent line. You take that value and plug it into the function to create a new point. You then write the tangent line for that. You find its x-intercept. You plug that in to the function, and you write a new tangent line. And you keep doing this over and over and over again. And as you go, ideally, you're going to be getting closer and closer and closer to that x-intercept, to your solution. Is everybody okay with that idea? So the formula for that is that your next x-intercept is equal to the previous x-intercept minus this quotient. The function evaluated at that previous x-intercept divided by the derivative of your function evaluated at that previous x-intercept. So let's just kind of show you where this formula is coming from. Does that sound good to you guys? Yeah. This is like a derivation or like a proof. It's not something I would expect you to repeat, but in a course like this, it's important that you kind of see where these things come from, that it's not magic. So what I'm going to do is I'm just going to show us how we get x2. Okay? So what I'm going to do is I'm going to start by writing with x1 and writing the tangent line for that. So y minus f of x1 equals the slope for that tangent line, which is f prime of x1 times x minus x1. So let's see, we'll distribute that derivative through and then add the f of x1 over to the other side. We're looking for the x-intercept, so we're going to set that equal to 0. Now, we're trying to solve this for x. So we want that guy. So we're going to add over f prime of x1 times x1, and then subtract over f of x1 and we'll divide both sides by this, which is write it this way. So those guys cancel. Those guys cancel. We have x1 minus f of x1 over f prime of x1 equals x. And this is really x2 now, right? Because that's our x-intercept. And that is exactly that formula, just where xn is x1 and xn plus 1 is x2. And if you repeated the same work that we just did and you used xn's and xn plus 1's, you'd have the exact formula we have there, right? Chanel.
So wait, so I'm confused. Why did you put x2 on that side and x1 on that side? On the right side, x1 and x2 on the left side.
I mean, it's the same equation, and just the equal sign is on the left instead of the right.
Okay.
Right?
So,
isn't this the same thing as what I have over there?
so it doesn't matter which side it is? Like,
Well, it's like if I have A equals B, doesn't B equal A?
yeah.
That's all, that's what we have,
Okay, got it.
right? Like, that's it. That's okay? Okay. And so the idea here then is, for some x-intercept r, if I do this iterative formula or this iterative process infinitely many times, eventually the x-intercept that I find is going to be the x-intercept for the function. It's going to be r, right? We're getting closer and closer to r each time I take an iteration. If I do this infinitely many times, I should definitely get to r. Pierce.
Will it give you R, like in the problem, like it'll say like this is what you're trying to get?
No, but we'll look at the examples and you'll see like what to do with it. It's pretty clear from the wording in the example what they want. Braden?
Is it possible to actually skip over R?
Yeah, so here's the thing. Let's look at an example of when Newton's method kind of fails, right? So let's take this as an example. So we pick our x1. So there's our thing. We do our tangent line. There's our x2. So we go to this point, and now we draw our next tangent line. x3 is not over there. So to get you see what's going on is we're just like jumping back and forth across it, right? So remember when we do this on your calculator, what is the first thing the calculator asks you for? A left bound and a right bound, correct? Because what the calculator doesn't want to have happen is what's happening here, where you're shooting off way past this. I suspect, again, I haven't dug into the programming, what the left and right bound is doing is if your x-intercept is past the left bound, just like, we're not using that, we're just using the left bound. Or if your x-intercept goes way past the right bound, it says, we're not using that one, just use the right bound. And it keeps it from ever getting too far away from the x-intercept. Now, I suspect that if you do this infinitely many times, you're still going to end up at the x-intercept, but it may not be real pretty getting there. So that initial choice can have a big impact of like, how many times do I really have to do this process? And that's kind of the takeaway here, is that it is going to be sensitive to that initial choice. And if you have lots of x-intercepts, finding the one that you want, again, that initial choice will make a big difference. Everybody's okay with that? Again, if you think about on the calculator, when you do that x-intercept command, you do left bound, right bound, and guess. And if you have 2 or 3 or 4 x-intercepts on there, the guess really matters, right? Like if there's 2 and you pick somewhere in between, it's not always clear which one it's going to find first. It's not necessarily the one it's closest to. Okay. So let's look at doing this process now specifically. Like we've kind of talked about the formula. We've talked about kind of how the process works. Let's actually do some numeric examples and do this by hand here. So again, you need to pretend like we're in our time machine and you're like Isaac Newton in the 1700s, or no, 1600s, and there are no computers and there are no calculators and like, you know, you still have an abacus and a compass and straight edge. Yes, you have all the technology of a 16th century scholar. You know the Isaac Newton story, right? Well, no, I'm like that. Well, there's that, yes. But so he's a student at I forget the college in England, Trinity. But the plague breaks out, and he goes back home to the countryside to like get out of the city, and basically like locks himself in a room for like a year. And when he comes out, he has like Newtonian physics finished, calculus finished, optics finished, like just comes like incredibly productive, like the most productive intellectual year in history with what he was able to accomplish, just like locked in his room by himself. I had to be reminded to feed himself. Like his parents were taking him meals and like, you need to eat. You haven't left your room. Well, that's the beauty of like mathematics and stuff is like, you know, because you proved it.
Yeah, but like if he created stuff, figured it out.
Well, he invented calculus specifically to do physics. Like it was him trying to like describe the motion of things like in space, like of the planets. It's like I need to figure out how this works. And to figure out gravity, he needed calculus, even though he didn't really figure out gravity.
You did it?
No, Einstein finished that. With like the gravity is like curved space-time. Newton didn't come up with that. But what he did is like it works almost all the time. He is really very close. Really very close. And for the tools he had available to him, it was as close as you conceivably could have gotten. Like he didn't have the tools available to see that there was something else going on. Anyways, so let's finish that, or do an example here. So it says, starting with x1 equal to 2, find the third approximation, that is x3, to the root of the equation x cubed minus 2x minus 5 equal to 0. So our f of x is just going to be the equation that's equal to 0. We need f prime of x, which would be 3x squared minus 2. Good. And now x1, we're told, is 2. So x2 is going to equal x1 minus f of x1 over f prime of x1. So if we fill that in, that's 2 minus 8 minus 4 minus 5 is negative 1 over 12 minus 2, that's 10. So 21 over 10, or 2.1.
Is that it? That what you do?
Well, now we have to do x3, which is just taking our previous answer and plugging it back into the formula. Now, I'm not going to do that by hand because just like fractions and cubing and like common denominator is just going to be a big hassle. Yeah, Pierce, what's up, buddy?
What x value are you plugging in for the x2 thing? Oh wait,
Yes, it does say x1. So we do that, and again, I'm just like kind of plugging that into my calculator because woof. You get that. But here's the beautiful part about this process. With our modern graphing calculator, this works really, really well. So let's do this with the calculator. And the time it takes me to do like 10 iterations on the calculator is probably about 3 seconds. Just have to set it up. So this is the way that we're going to do this on the calculator. And if you have your calculator with you, I encourage you to take it out so you can follow along. But this is a lovely, lovely, lovely process. So I'm going to start by typing f into y1 and f prime into y2. So I'm press y equals, and I'm going to, in y1, I'm going to do x cubed minus 2x minus 5. And in y2, we'll do 3x squared minus 2. Everybody's good? Going to exit out of there. I'm going to type in my x1, my starting x value, and then just press enter. And now what I'm going to do is I'm going to type in that formula that we were given before. So where it says xn, I'm going to use ants, the ants command on my calculator. So that's second and then negative sign. Then I have minus. I'm going to do y1 because that's what I stored f. So to get to y1, I press vars, which is right under the down arrow. And we'll go to y vars, pick function, pick y1, and I'm plugging ants into y1 and divided by now the derivative, which I stored into y2. So I'll do vars, y vars, function y2 of ants, and then I'm going to press enter. And then I'll press enter again. And I can just keep pressing enter over and over again, and it keeps taking my previous answer and plugging it into the formula I typed in. So it's just doing Newton's method. And you saw here, notice that if I did this like 5 times here real quick, what do you notice about my answer here? What's that telling you? That is actually the solution, right? Or at least as close as your calculator can get to the solution with the decimal points it carries. Yeah, Prater.
Stopped at the one right before the 2.09.
Yeah, that's what I had. So I don't know. I pressed enter like. Oh, okay. Yours, you got a different answer. I suspect then like you fat fingered something up here.
Yeah.
That's my best guess. Did you do like 3x squared negative 2 and not minus 2 or something?
Apparently, my eyes are messed up, and apparently I didn't got the right answer, just my cat texted.
Oh, okay.
Yeah.
Oh.
I misread your answer.
That's okay. It's okay. Ava, did you get it? You're looking around like, okay.
Yes.
All right. Everybody's happy with that? Isn't that lovely? Like I can just rip through like 5, 10, 20 iterations on my calculator, like whatever. Just set it up and rip. Let's do another example. So here we're asked to find an approximation correct to 8 decimal places for the 6th root of 2. Now, in Newton's day, how would he do this? Compass and straight edge are constructing, like a 6-sided figure, and you're looking at like it's terrible. It's a terrible, tedious, long process where like accuracy counts and then you're measuring. It's not a whole lot of fun. Here, what we would do, okay, just going to think about the 6th root of 2 equaling some x. Now, I'm going to, like do the 6th power to both sides and then move everything onto one side. So there's my f of x and my derivative. Chanel?
Why should it get equal to x?
Well, it says it wants to know what the 6th root of 2 is.
Okay.
Right, what's my variable?
X.
What the 6th root of 2 is, so that's why I had it equal that, right?
Okay, thank you.
Uh-huh. Okay. So now I need a guess. Terrible guesses.
0.
Terrible guesses. 1 is a great guess, Emma.
Yeah.
Because I know that the 6th root has to be bigger than 0 and less than 2. What's the best number I could pick between 0 and 2?
1.
I'm picking 1, right? Like that makes the arithmetic much easier. Everybody's okay with that? All right. Calculator time. So the only thing I really need to do is I need to update my y1 to be x to the 6th minus 2. And update my y2, 6x to the 5th. Yes, Chanel.
Oh, sorry. Why did you say between 1 and 2? Is it because it's the 6th root of 2?
Well, like, it's a 6th root. It has to be between 0 and 2.
Okay.
Because if it's a 6th root, it has to be positive.
Okay.
Because you're doing it to a positive number.
Okay.
And it has to be smaller than itself.
Okay.
Because if you do any root, the number is getting smaller,
Okay.
right?
Alright.
So I pick a number between 0 and 2 that you want to use. I mean, I'm picking 1, right? Like, did you have to pick 1? No, but like goodness sakes, like make your lives easier. All right, now watch this. So we updated our equations. I'm pressing 1, enter. And then I'm just going back up and grabbing my formula.
Wow.
And then press enter.
It's like magic.
So I got 1.116. I press enter again. I am correct to 1 decimal place because the first decimal is now constant. I'll press it again. I'm correct to 2 decimal places because the first 2 decimal places are the same between the previous things. Now I'm correct. Ooh, I'm all the way up to 4 decimal places. Everybody see what's going on? I'll do it again. Now I'm correct up to 1, 2, 3, 4, 5, 7 decimal places. And that's now past 8. Everybody feel happy there? Okay. All right. Last example. It says find, correct to 6 decimal places, the root of the equation, cosine of x is equal to x. What's my f of x going to be here? Great, cosine x minus x, because we want to get everything onto one side. Could have you done x minus cosine x?
Yeah.
Sure, if you want to. It doesn't matter. What's the derivative then going to be?
Sine
negative sine x minus 1. Good memories. And what should our first x be?
Pi.
Pi?
One. 0.
I just do 1.
Wait, what does it have to be between this time?
It does. Well, here it's much less clear, right?
Yeah.
What it would have to be between.
Pick a value.
To some extent, yes, just pick a value, right? Like I know that when x gets really big, cosine is stuck between -1 and +1, right?
Oh, that's true. Yeah.
So if x gets really big or really small, obviously there's no solutions out there because they have to be equal. You know, cosine x and x have to be equal to be 0.
Okay.
So I don't know. 1 feels okay to me. 0 is probably going to be fine.
So
Pi maybe is going the wrong direction. That might be too big.
But yeah, this one should generally be between -1 and 1 because like is that cosine's like
Yeah, that's kind of where I'm thinking.
okay.
So again, all I'm doing is going in and updating my y1 and y2 on my calculator. Which is, I really love because it's like, takes just a second. Type in my new guess. That's easy. Go back and grab my equation that I've been using. And then we're just gonna cosine it? Oh, yeah, there. It's like, why isn't that it's so dumb? Minus x. It's like, that's not the what the back of the book had. My first derivative?
Well, I mean like sine squared x.
Derivative of cosine is just negative sine.
Oh shoot.
That's okay. No, it's okay. Like, just, you're not sure, answer or ask. And again, we're going 6 decimal places, right? So this is my guess 2. This is my x2. There's x3. I have 1 decimal point. There's x4. I have 3 decimal points. There's x5. I have 6. So I'm done. What do you guys think? This is not bad, right? This calculator's doing like almost all the heavy lifting for me, which thank you very much, calculator.
It's not too intense.
No, it's a pretty good one to start the semester with, right? Like, worst case scenario, what's the most calculus we really had to do? Oh, I had to take the derivative of polynomials and then like 1 trig. Like, yeah, it's okay. It'll be all right. You can do that. It should be easy derivatives. But like, okay. So again, handful of homework problems for you to try. For the most part, use your calculator. Some of them you have to play around a little bit with the guesses to get what you're looking for. That's the point, is to see that like, for some of these, like coming up with that first guess is like kind of a hassle because it's a lot of guessing. It is literally guessing. And that's okay. So if you have to try a bunch of different guesses and you keep getting the same answer when it's like there's supposed to be 3 different answers, I can only get 2 of them. You know, like you can cheat a little bit and like graph the thing to find out where that third answer is to maybe help inform your guess. But that's the idea. Now, if you're really inclined, what could you do to help yourself in terms of coming up with like a guess? Think about calculate. Imagine you're Newton and you don't have a graphing calculator.
Yeah.
I would use my derivative tests, is what I would do. I'd locate the maxes and mins and see if there's a change in sign between my max and min, because that tells me, okay, if this went from negative to positive here, I had to cross the x-axis somewhere. So let's pick a guess in between these guys. And I know for it to change direction from positive to negative, I have to be at an extrema. So like that's what you would have done if you were calculatorless. You would do first and second derivative tests to come up with, okay, in between these two, I have to have a solution. And then do a Newton's method to approximate that solution. Now, we wouldn't have to be that obtuse because we have a graphing calculator, but like, that's what you would have done, or what Newton would have done. Is everybody cool? It feels like enough for today. Tomorrow, we start our journey into integration with talking about antiderivatives.
Is that hard?
No. Was it? Well, it depends. It can be very hard. It won't be at the start.
Okay. So are integrals in general easier or harder than derivatives? Like for this course?
So here's what I would say in general. Doing the derivative of something can be really can get really complicated, but it's always going to be possible for you, right? Like I can make it terrible and have like chain rules nested inside of quotient rules, nested inside of product rule, and like a bunch of stuff going on, but you can still do it. I can give you an integral that you just can't do.
Oh, really?
But in general, like the integration is going to be easier than a derivative in general, but like specifically I should say, integrals will be easier than derivatives. But like in general, it's a much, much harder problem because there are integrals that like, there is just not an algebraic technique to do this. What you have to do is like an approximation technique.
Are we do
You don't go that far
Oh.
unless you're like going to be a math major, a statistics major or something. So like a lot of probability calculation in practice is done using a method called like a Markov chain Monte Carlo method, where essentially you're using a data set to approximate a probability distribution and then using that to calculate your probabilities, because you just can't do the integral that you want. It's not as hard as it sounds. The computer handles like all of it.
Alright. There's no homework quiz tomorrow, right?
If there is, it would be from review things from first semester.